Hello, and in this video we're going to be continuing our work with collisions, but in this part we're going to be looking at a ball now colliding with a surface, so a wall or a floor. Okay, and before I start, I want to say that you do need to be comfortable with your SUVAT equations from normal maths. Okay, so I highly recommend, if you haven't already, to have a look at year 1 mechanics from pure maths. A look at the SUVAT section. Okay, but hopefully you covered that already. And as a reminder, it's these equations here. They're in the formula book, but hopefully you are aware of how to use it. Okay, we will be looking at this a bit later on. Okay, this will be important. But there we are. Okay, so let's have a look at this then. So, as I said, we're going to be looking at a ball or particle or an object bashing into a wall. Okay, and so you can see that here. Hopefully, the visuals hopefully can help with that. Hopefully, you can see that. So, what we're going to be looking at is, again, considering the speeds. So, let's take this example here. So, we have a ball that's going to go into a wall, and so it has so before the collision, so before the ball hits the wall, it's going to have a speed u, and then it's going to rebound backwards with a speed v. So this is before and after the collision, right? And so we can express e here as the well, last time we saw it was the speed of separation over speed of approach, but generally the gist was it was the speed after over the speed before. So we can say that, okay, as the speed after over speed before. Okay, and actually this is quite nice. Okay, there's no complications with this because it's very because simply we could say in this, if I was to use these letters, it'd be v over u. Okay, so what I do to work out the coefficient restitution here is we divide the rebound speed, so the speed after, by the speed before, and there's only two speeds. Okay, it's more simpler than last time because there's only one particle now, there's not two. So coefficient restitution is dead easy to work out in this case, dead easy. Okay, and so there we are. Okay, so I just want to have a look at some examples how to calculate and work with e here. Okay, so e then, so okay, it's a really wordy question, but hopefully you can see essentially this situation here. We've got a ball that's been that's going to hit into a wall. Okay, anyway, so e then in this case, well, before the collision, it has speed 8. Then after the collision, it has speed 2. So if we divide the speed after, which is 2, divided by the speed before, which is 8, that's e. Okay, we can simplify that to a quarter. Okay, so there we are. So now we've got these examples, and now it's very similar, but now we kind of need to work in reverse because we're given e and we need to work out the speeds in these two cases. Okay, so if I have a look at part A, so again, before the collision it has speed 7, then afterwards it has speed v. So e is going to be the final speed v over the initial speed 7. Now, we know that e is a half. We're told e is a half. So a half equals v over 7. Then we just solve for v. So we can cross multiply. So that'll be 7 over 2 equals v. Okay. And there we are. That is my final speed there. Then in part B, e, well, before the impact has speed u, then afterwards it has speed 6. So e is going to be 6 over u. Okay, but we're told that e is 3/4. So 3/4 is going to equal 6 over u, and then we just solve for u. So we can cross multiply. So then we can say 3u is 4 times 6. So that will be 24. Therefore, u is 24 over 3. And that is going to be 8. Okay. and that is my initial speed there. So hopefully you are comfortable with how I calculate E here. So it's more simpler than before, but there we are. Okay, then we got this question here. Now it's a worded question, so we're going to need to draw a diagram ourselves. But it says a small sphere collides normally with a fixed vertical wall. Before the impact, the sphere is moving with a speed of 4 on a smooth horizontal floor. The coefficient of restitution is 0.2. Find the speed after the collision. Okay, so we're going to draw a diagram. So we've got a vertical wall. Okay, so it's going to be a sort of wall, sort of something like this, which is vertical, right? It goes up. And so then we're told we have this sphere here, okay, and it's going to collide into the wall. So it's going to go into the wall like this. Now before the impact, it has speed 4. So 4 before, okay, then afterwards it's going to rebound backwards, okay, and that's going to be a speed of V afterwards. Okay, hopefully happy with this. Okay, we're also told that E is 0.2. Right, so if we calculate the restitution here, well, that's going to be the final speed V over the initial speed 4. Okay, but we also know E is 0.2. So if we sub that in, we get 0.2 is V over 4. Then we just multiply by 4 to say that V is 0.8. And there we are. Okay, so that's just that's the main idea, right? So we divide the final speed over the initial speed. Cool. Okay, now we're going to be looking at when the ball starts to fall down, okay, or moves up. Okay, so the movement's now going to look a bit like this. Okay, so as you can see here, we've got this ball that now moves up and down. It bounces up and down on the floor. Okay, that's going to involve SUVAT. Okay, so now we're going to be involving SUVAT, which again, as I remind you, you need to be comfortable with from normal maths. Okay, so as a brief reminder, again, these are my SUVAT equations. We're going to be looking at things falling down and bouncing up. Okay, as a general sort of example, let's say have a ball here, and then the ball eventually hits the ground here. Okay, so this is my ground. So then it's going to have an initial speed U downwards, okay, and then a final speed V. Okay, now the distance is going to be F, okay, and obviously the time taken for it to fall is going to be T. And so that's what these SUVAT equations will tell us. So S here is my distance, V is my final speed, U is my initial speed, and T is the time taken. Okay, so I can use the SUVAT equations to work out any missing quantities. Now the last thing that is missing is A, the acceleration. Okay, now when things are falling down in what we call free fall, the acceleration is quite unique. The acceleration downwards, so when things are falling down, the acceleration is G. Okay, remember G was this 9.8, okay, which hopefully you're familiar with. We looked at that in chapter 2 as well, in the work energy power chapter. So you should be quite comfortable with the idea that acceleration downwards when things are falling down due to gravity or whatnot, the acceleration is G. Okay, and usually that's 9.8. Okay, and so there we are. So hopefully happy with this setup. Okay, so this is sort of the general sort of scenario, and we can use SUVAT to work out any of these missing quantities. Okay, now before we look into an example related to restitution, we're going to be looking at a sort of revision question from normal maths. Okay, so just to really have a good grasp of these SUVAT equations, okay, because that's going to be the main bulk of these questions, okay, so we need to be proficient with it. Okay, so this is from normal maths. So we're told a book falls off the top shelf of a bookcase. The shelf is 1.4 meters above a wooden floor. Find the time taken. From the time taken, the book takes to reach the floor firstly. Okay, so remember we're going to draw a scenario. So what's happening here is we have some bookshelf here, and then we got a book which I'm going to draw as a little dot like this. Okay, nothing fancy. So that's my book. It's going to fall down. Okay, and then it's going to hit the floor, which is all the way here. Okay, so hopefully happy with that. So we got the so this is my shelf, okay, and then the ball, the book here, which is my dot, is going to fall downwards towards the floor. Okay, hopefully happy with that. So well, firstly, this is going to be my height. So from the shelf to the floor, that's my height, or my distance, if you will. Okay, and so then the initial speed, so the speed when it first leaves the shelf, well, it's going to start with 0 speed, right? And then it's going to hit the floor here, and then it's going to have a final speed v. Okay. Okay, so hopefully happy with that. Now I'm told the shelf is 1.4 meters above the floor, so actually the height is just 1.4 here. Okay, I can add that on. And so now I can use my SUVAT equations. Oh, and lastly, the acceleration. Remember, it's going to be g here, okay, or 9.8. Okay. And so now I can use my SUVAT equations to work out the missing stuff I want to find. So firstly, it wants the time taken to reach the floor. So what I'm going to do, I'm going to label my S, my U, my V, my A and my T. Okay, so what do I know? S, which is my distance, so it's going 1.4 downwards. U, that's my initial speed, which is 0. V is my final speed. I'll leave it there for now. A, now A is acceleration 9.8, which is G, and T, I also don't know. That's what I want to find. I want to find the time taken. Okay, so I'm going to put a question mark there. So I have now 4 things to consider. I want to deal with S, U, A, and T. Okay, hopefully you're happy up to here. So now I'm going to look at my SUVAT equations. Which of these 5 equations does not include V? Okay, I'm not interested in V here. Well, it's going to be this one, isn't it? It's going to be S is UT add a half AT squared. So I'm going to use S is UT plus a half AT squared. And then I can work out T, because now if I sub my values in, so S is 1.4, it's going to equal 0 lots of T, add a half lots of 9.8, lots of T squared. So this simplifies to 1.4 equals 4.9 T squared. And then you can see how I'm going to get T squared from this. So therefore T squared, if I divide by 4.9, I get T squared to be 2/7, okay, and then I can just square root it. So therefore T is the root of this, and that's going to be 0.53 seconds to 2 decimal places, and that's the time taken. Okay, then in part B, it wants the speed when it strikes the floor, so it wants the final speed here then, right? So now we need to look back at our results, and actually now I want to work out V. So I know S, U and A. I also know T now as well, but I'm going to deal with S, U, V and A now. Okay, so what equation does not include T here? It's going to be this one, isn't it? It's going to be V squared is U squared plus 2AS. Okay, so V squared is U squared plus 2AS. So therefore v squared is going to be u squared, which is 0, all squared, add 2 lots of a, which is 9.8, lots of s, which was 1.4. Okay, therefore if I simplify this, I get v squared to be 27.44. And lastly, if I square root that, that's going to get me 5.24 meters per second to do two decimal places. Okay. Okay, now we're going to be adding coefficient of restitution into the mix. So here we're told a particle falls 3 meters from rest onto a smooth horizontal plane, it then rebounds to a height h. The coefficient of restitution is 0.25. Find h. Okay, so what's happening here? So we have this particle that's going to fall towards a floor. Okay, it mentions a horizontal plane. Just a fancy word for saying a floor, pretty much. Okay, so we have this particle, let's say here, then it's gonna hit a floor, say here, right? So it's gonna hit the floor at the end here, so hopefully you're happy with that. So it falls down to a floor. Now I'm told it starts from rest, so the initial speed is going to be 0 here. Okay, and then it's going to then hit the floor with a final speed v. Okay, now I'm also told the particle falls 3 meters down, so the whole height or the distance here is going to be 3 meters. Okay, hopefully happy with this. Now the last thing to include is the acceleration. Now remember, the acceleration is 9.8 downwards. Okay, and there we are. So hopefully happy with this. So if I well, I'm going to use SUVAT here. So if I label my information, s, my distance is 3, my initial speed u is 0, v is well, v, right? Let's just leave that. A is going to be 9.8, and t, again, I don't know anything about t. Now I'll give you a hint. We're going to need to, it's going to be, we're going to need to work out v, not t here. Okay, we're not interested in time. Why? Because the question involves restitution. And what does restitution involve? It involves speed. Okay, so we're going to need to work out the speed here to use that. Okay, so there we are. So we don't care about t, so v here. So the equation, my SUVAT equation that does not include t, is going to be, again, v squared is u squared plus 2as. So if I apply that here, so that means v squared is going to be 0 squared for u, so 0 minus 4, sorry, where's that come from? 0 squared plus 2 lots of 9.8 for a and 3 for s. Okay, so v squared is going to be, if I simplify this, 58.8. Okay, then I can root that. I can square root this to get v. Okay, and that will be 7.67 there to 2 decimal places, and there we are. That is my final speed there. Okay, or in other words, the speed as it hits the ground. Okay, so v here 7.67. Okay, now what's happening then? What's happening? Well, we're told the particle then rebounds. So what's going to happen is the ball then is going to bounce off the floor and bounce up. So if I now add this diagram here, we've got the situation where the ball is now going to then bounce up off the floor. Okay, and so it's going to bounce up to some height. Okay, some height h there. Okay, now as for speeds, now it's going to rebound off the floor with a speed I'm going to call U dash. Okay, that's going to be my new initial speed here. So it's going to bounce off the floor with a new speed, which is U dash. But then it's going to go up, up and up. It's going to bounce up and up. It's going to move up. But then it's going to want to come back down. There's going to be a point where it's going to then reach 0 speed. Okay, think about it in real life. Think about bouncing a ball off a floor. It's going to go up and down and up and down, but the point is it already go up so high, then it reaches 0 speed, then it comes back down. That's what's happening here. Okay, so the ball's going up to this height h, and then it has to reach 0 speed. Okay, so hopefully happy with that. Okay. Okay, so hopefully happy with the speeds here and the situation going on. Again, the acceleration downwards is 9.8. Right. So, if we try and apply SUVAT here, so again, if I label my information, S is now H, okay, my distance H upwards. U, now the initial speed I'm going to call U dash. V, well, the final speed at the end here goes to 0, then A again. Now, A. We're now going upwards, okay? We're considering upwards now, okay? But the issue is the acceleration is downwards. It's due to gravity. It's acting downwards. So it's sort of in the negative direction, right? Because now we're taking upwards as positive because we're going up. So we're going to need to make it negative 9.8, okay? And there we are. And again, we don't care about T here. And I don't know T. And so there we are. So this is the information I have. Now, I want to work out H. But the issue is I also don't know the initial speed U dash here. But I can work it out because I can consider restitution. So I'm told E is 0.25. So what I'm going to do, if E is 0.25, that's telling me the information about the speeds before and after it hits the floor, right? And so we've got this situation again. So if I draw the situation out to illustrate, so the ball's going to hit the floor like this. So it's going to go towards the floor. It's going to hit the floor with this speed 7.67, right? And then it's going to bounce up off the floor with this speed U dash. Okay, hopefully happy with that. So these are the speeds before and after it hits the floor. Okay, hopefully you can see that here. Okay, the before and after. Hopefully that makes sense. So now so if I was to work out E here, so that's going to be my after speed, which is U dash, over my before speed 7.67. But I also know that E is 0.25, so I can sub that in and then times across to get U dash to be 0.25 times 7.67, and that would be 1.92. Okay, two decimal places, and there we are. That's my U dash there. So now I can use that in my SUVAT here. So that U is 1.92. So now I can work out H. Again, I'm going to use V squared is U squared with 2AS. So V is 0. So 0 is going to be 1.92 squared plus 2 lots of minus 9.8 lots of H. Okay, then I can just solve this for H. So if I simplify this, I'm going to get minus 3.6864 is going to equal minus 19.6 H. Then I can just divide. So H is going to be 3.6864 over 19.6. So then I get H to be 0.188 meters to 3 decimal places. Okay, And there we are. That is the value of h, okay? So that's generally the idea. That is the idea. So we want to consider before and after it hits the floor like this. So we split it into two parts like this. And then we use the restitution to work out the speeds before and after it hits the ground. Okay. So there we are. Okay, then in part B it says, without further calculation, state how we answer to part A would change if E is greater than 0.25. So if E increases now, so let's have a think. So part B, so if E increases the coefficient of restitution, now what's the coefficient of restitution telling us? It tells me how much, like, it basically tells me how much speed is lost, right? Or in other words, it tells me how bouncy the collision is. So if E increases, that means there's less speed loss. So that means the collision is more bouncy. And so that means the rebound speed is higher. Okay, so the speed so the speed the ball bounces up with is going to be higher. So the after speed, right? Which was u dash. Now, think about it. If we're leaving with a higher speed, if it's a more bouncy collision, then it has to reach a higher height. Okay, so therefore, reaches a higher height, or reaches a higher distance upwards. And so therefore h increases, right? So the height it goes up increases. And there we are. So my answer would increase. Hopefully that made sense. So the idea is that if E increases, it's more bouncy. And so it will bounce up even higher. So the height increases. Now we've got this question here. Pretty similar. So we have a particle and then it falls onto a floor. Okay, so we have a floor here. There we are. And so initially it's at rest. So initially has speed 0. And then it's going to hit the floor with a speed of v, let's call it. Okay. Now we're told it falls 22.5 centimeters. So that's my height or distance, if you will. Now, centimeters is an issue. Okay. It has to be in meters. Okay. It's what we call SI units. So the units have to be a specific unit. So it has to be meters here for length. Now in meters, that's going to be 0.225 meters, because obviously you divide by 100, since 1 meter is 100 centimeters. Okay, so we divide by 100 there to get it in meters. Okay, so that's my distance, 0.225. Now, there we are. So again, the acceleration downwards is 9.8. So if I label my information here, S is going to be 0.225, U is going to be 0, V is what I want to work out, and A is going to be 9.8. I don't care about T here, so I'm going to leave it there. So again, I can use V squared is U squared plus 2AS to work out V. Therefore, V squared is going to be 0 squared, 2 lots of 9.8 and 0.225. And so therefore, V squared is going to be, if I simplify this, 4.41. Okay. And so if I root that, I get V to be 2.1 quite nicely. So there we are. So I can add that on to my diagram if you want. So 2.1 here. Now, obviously, again, it's going to rebound. So now it's going to be this situation where the particle's now going to bounce upwards. Okay. And then eventually it's going to come to, then it's not going to go up any higher. And so eventually it's going to reach a speed of 0. Okay. and then I can call the speed initially as it bounces off the floor U dash. Okay. So hopefully happy with that. Again, the acceleration downwards is 9.8. Now, it wants me to find the coefficient of restitution. Oh, I know the height as well. So I know the height here is 10 centimeters, so it's going to be 0.1 meters. So that's how high it rebounds up. Okay, so hopefully happy with this diagram. Okay, so there we are. Again, I can label this part 1 and part 2 to clearly distinguish the two different parts of the motion. Okay. So in now, of course, I can work out U dash by considering. Actually, no, I don't know what the restitution is. It wants me to work out the coefficient of restitution. Okay, so I can't use that. So if I label my information, so S here is going to be the height 0.1. U is going to be U dash. V 0 and A. Now again, we're going upwards here. So this is going upwards. So it's going to be negative 9.8 because the acceleration is downwards. Okay. So now again, I'm going to use V squared is U squared plus 2AS. But now V0, that's going to equal U dash squared plus 2 lots of minus 9.8 lots of 0.1. So we can solve for U dash here. I can solve for U dash. Okay. So that means U dash squared is going to equal 1.96. Okay. Then I can root that to say that U dash is going to be 1.4. Okay, and that is my speed there. Okay, so I can add that on. So it rebounds with speed 1.4. So I can now work out the coefficient of restitution, right? Because if I draw the situation as it hits the floor, okay, it bounces to the floor. It hits the floor with speed v, which is 2.1. Then it bounces up with speed 1.4. Okay. So E in this case is going to be E is going to be the final speed, which is 1.4. So that's afterwards divided by 2.1. Okay. So that simplifies to 2/3. Okay, and so that is my coefficient of restitution then. Okay, now we're going to be looking at multiple bounces off the floor. Okay, now technically the way the book does it, it's done. This is done in the final part in chapter 4.4, where we look at multiple collisions. But I do think it makes a lot more sense and it's more ordered to do it here now. I think whilst we're already looking at bounces off a floor. Anyway, so we're going to look at these questions here. So here we're told a small smooth sphere falls from rest onto a smooth horizontal plane and rebounds off from the plane. It takes 2 seconds to reach the plane, then another 2 seconds to reach the plane a second time. Find the coefficient of restitution. Okay, so what's going on here? So again, we've got this this particle that's falling towards a floor. So again, let's say we have the particle or the sphere here, then it's going to hit a floor down here, right? And so then it falls from rest. So initially the speed is 0. Okay. And then it's going to hit the floor with a speed of v. Okay. I'm not really told the height here, the distance it falls. I'm not told that here, but what I am told is that it takes 2 seconds to reach the floor. So I know that the time is 2 here. T's 2. So now I don't know the distance, but I know time. Okay. So if and also lastly, the acceleration, of course, is 9.8 downwards. and there we are. Okay. So if I label my information here, S, I don't know anything about. U, my initial speed is 0. V is, well, I'm going to want to work that out, most likely. A is going to be 9.8, and T is 2. Okay, and so there we are. So I don't care about S. I want to find my final speed. With these questions, you are going to want to find your speeds, because then you can apply restitution. So a little tip there with these questions. So consider the speeds. So which equation does not involve S for my SUVAT equations up here? Hopefully stare at them. You can see it's this one we're going to want to use. That doesn't have S. So V is UT. No. V is U plus AT. There we are. V is U plus AT. So therefore I can say that V is going to be 0 plus 9.8 lots of 2. So very simply I get V to be 19.6. And there we are. Okay, but then of course the ball will bounce up off the floor. So now we have this situation. So the ball is now going to bounce up like this. And then obviously it's going to reach a point with 0 speed. Okay. And then it's going to rebound off the floor with some initial speed U dash. So there we are. Of course the acceleration is going to be 9.8 downwards. So that's my gravity G. Now, I'm still not given any information about distances, but what I am told is that it takes another 2 seconds to reach the floor a second time. So that's telling me the whole time between when it bounces off the floor to when it then hits the floor again is 2 seconds. So in other words, obviously the particle goes up, but then it's going to come back down. Okay, so we've got this situation here, but then the particle will come back down to the floor. Okay, and so the whole time between from when it leaves the floor to then when it hits the floor again, that whole time is 2 seconds. So it might be more useful to instead consider, if I get rid of this now, it might be useful to consider this as my initial and final point. Okay, so initially it leaves the floor, it leaves the floor, then finally when it returns back to the floor. Okay, and so I know that time, so it might be more useful to consider this. So if I, let's say, call this the final speed V dash here. Okay, now this is also useful because the displacement here, so this is S, right? So my SUVAT S is technically the displacement, remember? The displacement between these 2 points here is 0. Because remember, displacement is effectively how far I am away from the starting point. So if I start on the floor and end also on the floor, overall I've not really gone anywhere. So the displacement is 0. Okay, so S is 0. So now I can use SUVAT quite nicely. Okay, so S is going to be 0, U is going to be U dash, V is V dash, A. Now again, we're considering upwards as positive. Okay, upwards is positive. So technically it should be minus V dash, shouldn't it? Because the speed is going down, so it's minus V dash here as well. A is also then going to be minus 9.8. Because again, acceleration is also going downwards, and T is 2. Okay, so hopefully happy with that. Now, I can work out U or V here. Okay, I've got enough information. So let's just work out U. Okay, let's work out the initial speed here, U, the speed as it bounces up. So the equation that does not involve V is this equation here. So S is UT plus a half AT squared. So therefore 0 is going to be U dash times T. So it's going to be 2 lots of U dash plus a half lots of minus 9.8 lots of 2 squared. Okay. And so we can say 2u dash is going to be, if we solve for u dash, that's going to be 19.6. Therefore, u dash divided by 2, we get 9.8. And that is my rebound speed. Okay, that is my speed here. Okay, so 9.8. Okay, now we're in a position to actually work out what E is. Because now, if you remember here, this is my speed before it hits the floor. And this is my speed after it hits the floor. So if I consider the impact then with the floor, okay, so the ball hits the floor. So initially, as it hits the floor, the speed is 19.6, right? And then as it rebounds and it bounces off the floor, it's this 9.8 here. Okay, so therefore E is going to be the speed after, which is 9.8 divided by the speed before, 19.6. That will get me a half, and that is my coefficient of restitution there. Okay, so hopefully that made sense, and in particular, hopefully it made sense why here it was better to consider the point from when it leaves the ground to when it returns to the ground again, because we got the information that the whole time here is 2, so that allowed us to use SUVAT more effectively here. Okay, so we've got this question here, and it's going to be a lot more involved, and so I've got additional information here for this question. Okay, but let's have a look at it. So here we're told a small table tennis ball, which may be modelled as a particle, falls from rest at a height 40 centimetres onto a smooth horizontal table. The coefficient of restitution is 0.7. Find the height to which the ball rebounds after the first and second bounce. So again, we've got this situation where we've got this ball that's falling to a floor. Okay, so if we have this little ball here, then it's going to hit a floor like this. Okay, and so it starts from rest, it falls from rest. So initially the speed is 0. And then it's going to hit the floor with a speed v. Now I'm going to call this v0, okay, because we're going to be using a lot of u's and v's here, because there's multiple rebounds, multiple bounces. So I'm going to just number the v's and u's like this. You'll see why it's going to be useful later in the question. But there we are. So that's my final speed. Now, obviously the acceleration downwards is 9.8. I also know that the height it falls down here is 40 centimetres, or 0.4 metres. Okay, so there we are. So now, if we apply SUVAT, we can work out this final speed v0. So S is going to be 0.4, U is going to be 0, V is v0, and A is 9.8. I don't know about T and I don't care about T. I can work out V here. If I look at my SUVAT equations, I'm going to use V squared is U squared plus 2AS. That doesn't include T. So V squared is U squared plus 2AS. Therefore, V0 squared is going to be 0 squared at 2 lots of 9.8, lots of 0.4. And so V0 squared will be at 7.84. Okay. So if I root that, I get V0 to be 2.8. Okay. And that is my final speed here. So I can add that on here. Now, of course, then the ball's going to then bounce up off the floor. So now we've got this situation. So the ball's going to go back up. And then obviously it's going to then reach a speed of 0 in the air. And then obviously it's also going to rebound off the floor. I'm going to call that speed U1. Okay. to signify it's after the first bounce. Okay, so there we are. Of course, again, the acceleration downwards is 9.8. And the height, now the height is what it wants me to work out here. I'm going to call that H1. Okay, so if I list my SUVAT here, S is H1, U is U1, V, well, the final speed is 0, and A, because we're going upwards now, it's going to be minus 9.8, as again, it's going downwards in the negative direction. Okay, so there we are. Okay, so I'm going to need to, I want to work out H1, the height. So I'm gonna need to work out U. Okay, I can do that by using restitution. So again, I got my ball here. If I consider the speed before and after it hits the floor, well, before it's going to be 2.8, and afterwards it's going to be U1. Okay, so therefore E is going to be U1 divided by 2.8. But I also know, I'm told, that E is 0.7, my restitution, right? So E is 0.7, so therefore 0.7 is going to be U1 over 2.8. And so therefore U1, I'll do it here. If I solve this, if I cross multiply, U1 is going to be 2.8 times 0.7, which will be 1.96. Okay, and there we are. So I can add that on here. So now I can work out F here, my H1. So again, that's going to involve V squared is U squared plus 2AS. So therefore 0 is going to equal 1.96 squared plus 2 lots of minus 9.8 lots of H1. So if I solve this, then I get that 19.6 lots of H1 is going to be 3.8416 if I square the 1.96. So therefore H1, if I divide, I get H1 to be at 0.196, okay, meters. And there we are. So I can add that on as well. Cool. Okay, so that's my height after the first rebound, after the first bounce. But then it wants me to continue further and consider the second bounce. So what's going to happen then, of course, obviously, as we discussed, the ball will go up and then it's going to come back down. And so as you can imagine, if it ends with 0 speed, it's then going to start to come back down with 0 speed as well. So now we're considering it going back down. So now we've got this next scenario. So now we've got the ball coming down. Again, it's going to start with 0 speed. And then it's going to hit the floor with a new speed. I'm going to call that V1. So this is the final speed after the first bounce. And the height, now the height after, so this is after the first bounce, it's now going to be this. This is how far it will go down now, 0.196. Okay, hopefully happy with that. Again, the acceleration is 9.8. So now it's pretty much like the same. It's pretty much the same scenario. We're just doing the same stuff again. So now S is going to be 0.196. U is going to be 0. V is going to be V1. A is going to be 9.8. Therefore, V squared is V squared is U squared plus 2AS. So V1 squared now is going to be 2 lots of 0.196 times 9.8. So V1 squared is going to be 3.8416. So if I root that, I get V1, my final velocity V to be 1.96. Okay, quite nicely. Okay, and there we are. So I can add that on. But of course, it's then going to bounce back up. So now we've got this next scenario, which again is now going to go up. Okay, so then it's going to end up with 0 speed again. It's gonna go to rest up in the air, and then it's going to leave the. Then it's going to rebound with speed u2. So this is my initial speed after the second bounce. Now, okay. Again, it's then going to reach a height h2 now. Okay, so there we are. Again, acceleration is 9.8. So now, if I use SUVAT here, S is h2, U is u2, V is 0, and A is going to be minus 9.8, because now, again, we're going upwards. Okay, as positive. So the downward direction is negative. So there we are. But of course, we're going to need to work out u2. So we're going to need to work out this initial speed here. Again, we're going to be using restitution. So, for the second bounce now, so now it has speed 1.96 before, then afterwards the speed u2. Okay, I'll label this bounce 2. Okay, and I'll label this one bounce 1. Okay, if it helps. But there we are. Now, again, E is 0.7. So, E now is going to be U2 over 1.96. Therefore, 0.7 is going to be U2 over 1.96. So, therefore, U2, if I cross multiply, 0.7 times 1.96 is going to be 1.372. Okay, and there we are. So I can add that on. And there we are. So now I can work out S then. So again, V squared is U squared plus 2AS. So therefore, 0 is going to equal 1.372 squared plus 2 lots of minus 9.8 lots of H2 if I squeeze it on there. So therefore, 19.6 lots of H2 is going to equal 1.882384. So if I divide by 19.6, I get H to be 0.09604. Okay, and there we are. Okay, so I can add that on here. So that is now my height after the second bounce. And so there we are. There we are. Okay. Those are my heights after the first and second bounce. So I'm going to add that on here. So remember, H1 was after the first bounce, the height after the first bounce, the height is 0.196. Then H2 was 0.09604. Okay, so hopefully happy with that. If I also state here that the original height H0 was 0.4, right? Hopefully you can see as we keep bouncing the ball, the height it goes up decreases. Okay, so it starts with 0.4, then 0.196, then 0.096. Okay, and it follows this diagram. This is what's happening. This is the motion of the ball. Okay, so you can see as every time it bounces. Okay, and then it says in part B, find the total distance travelled by the ball before it comes to rest. Now, I'm actually going to do that after part C, because I think you'll actually understand it more after we look at part C. So part C then says find the total distance travelled by the ball before it comes to rest. Okay, this is why I've included this diagram here, to help illustrate what the motion will look like. So as you can see here, the ball goes down, then up, then down. So it goes down, then up, then down, then up, then down, and up and down. But you can see it starts to level off. Okay, it bounces up less and less higher each time. Okay, so the ball doesn't bounce up as much in each bounce. Okay, so the more bounces we have, the ball bounces less and less higher. Okay, hopefully you can see that. So what exactly happens with the heights and the distances? So okay, so remember, my first height is 0.4. It drops down by 0.4 meters. Then it drops down by 1.96 meters after the first bounce, right? Then after the second bounce, it will then drop by 0.09604. So I've labelled all the heights here. Okay, I've labelled these for a reason. So these are my 3 heights. So this is my initial height. Then this is my height after the first bounce. Then this is my height after the second bounce. Now I'm going to do it up here, actually. Let me list the heights here, okay? Let me list the heights. List of rebound heights. Let me list them, okay? So we had 0.4 originally, then it went to 0.196. Then it went to, after the second bounce, at 0.09604, and it will continue on. Okay, obviously you can see the heights decrease after each bounce. So it should say I should label this bounce 0, then this is bounce 1, and this is bounce 2. Hopefully happy with what I've done here. So I've listed the heights after each bounce. Okay, the height the ball goes up to. Obviously, you can see they're going down, but there's something more particular about this. This is a particular kind of sequence, as it turns out. So consider this. Let me just consider doing 0.196 divided by 0.4. Okay, if I work that out, I get 0.49. But if I also then do 0.09604 divided by 0.196, I also get 0.49. That's telling me, in other words, that to get from 0.4 to 0.196, I multiply by 0.49. Likewise, to get from 0.196 to 0.09604, I also multiply by 0.49. You can then imagine we're going to keep timesing by 0.49 to get to the next and next heights. Okay. And so, hopefully you can spot this is going to be a geometric sequence of heights. Okay, so this is going to be a geometric sequence. Okay, hopefully you can see that then, right? So the geometric sequence is 0.4, 0.196 and 0.09604. So we can tell that the common ratio is 0.49. Okay, and the initial term is 0.4, as you can see. And so if we want to consider the total distance travelled by the ball, okay, well, think about it. Let's break it step by step. So originally it drops down by 0.4, then it bounces up by 0.196, then it bounces down by 0.196, then bounces up by 0.09604. Hopefully you can tell that the distance is going to be, I'll do it down here, the total distance, okay, that's going to be my original 0.4, and then think about it. So I dropped that. So again, use this diagram to help. So initially I drop down, okay, but then I'm going to bounce up, then I'm going to bounce down by the same height, okay. So see it here. So I drop down by 0.4, but then I go, but then what's going to happen is I bounce up by 0.196, then I drop down by the same height. So afterwards, I'm going to need to double the 0.196 because I'm going to go up then down, okay. Then I'm also going to then go up and down by the next height, 0.09604, right? And that's going to continue, okay. So I'm going to then double every height because the idea is I drop down, then I go up, then down, then up, then down, then up, then down. Okay. So there we are. So hopefully happy with that. So I can say 0.4 add 2, and then I can factor 2 out of the 0.196, add the 0.0604. And so this is going to be a geometric sequence, a geometric series, sorry. So in this series, A is going to be 0.196 and R is going to be 0.49. Okay, that's my multiplier. So it's going to be 0.4 add. Now remember, this is going to be an infinite series. So remember, think back to normal maths. We're going to want to use the sum to infinity. Okay, so that's going to be A over 1 minus R. So in this case, it's going to be 2 lots of A over 1 minus R, which here is 0.4 at 2 lots of 0.196 over 1 minus 0.49. And so if I work all that out, I get my total distance, okay? And so I get 1.169 to 3 decimal places. So that is my total distance, okay? Hopefully happy with that. So yeah, it's quite interesting. The heights after each rebound, the heights form a geometric sequence. Okay, so if we want to find if we want to add up all the heights, we need to do the geometric series, right? So there we are. Okay, now we're going to look at part B. So then it says describe the subsequent motion of the ball. Now we know exactly what's happening to the heights. Okay, so now we can describe what's happening. So what's going to happen is the ball is going to rebound with the height upwards. No, as we just saw, the height of the ball in each bounce, it forms a geometric sequence. So what that means is, if we were to describe the motion here, so we could say the ball bounces up and down with the height after each bounce decreasing by a multiplier of 0.49. okay, so what I'm saying there is effectively the heights are being timed by 0.49, so the decreasing by 49%. okay, so in other words, decreasing by 49%. okay, after each bounce. Okay, so hopefully you can see that there. Okay, so yeah, you can see what it's much easier to do part C first, because then you can see exactly what's happening to the heights. Okay, that's what they're looking for there. Okay, and then in part D it says give one reason why my answer to part C was unrealistic. So in other words, why is the height decreasing in this way unrealistic? Now what we're also saying here is the ball's going to bounce infinitely many times, because the height, there's always going to be some height no matter how many times we bounce. If you keep multiplying by 0.49, it's going to get close to 0, but it's not going to ever be 0. Okay, so there's always going to be, no matter how many bounces we consider, there's always going to be a smither, a little bit of height it bounces to. That's not realistic, because that's suggesting infinite bounces. But obviously, you in real life, bounce a ball, it's not going to bounce forever. So that is the unrealistic part. So it's unrealistic because the model suggests the ball would bounce in forever. Okay. But of course that can't be true, because the ball would eventually just stop moving. It would stop bouncing, right? And there we are. There we are. Okay, so we're going to finish off with an exam question. They don't really ask this particular topic very often. So this is from the sample paper. So we're told a small ball of mass 0.1 is dropped from a point which is 2.4 meters above a horizontal floor. The ball falls freely under gravity, strikes the floor and bounces to a height of 0.6 above the floor. Balls modelled as a particle show that the coefficient restitution is 0.5. So okay, once again we've got this scenario where we've got a ball dropping down. So it's going to hit the floor like this. So there we are. Now, you can guess that the initial speed is again going to be 0. It's going to be it's going to be from rest. Now, they're quite subtle with it. They don't state it starts from rest. But the wording kind of implies it, because it said it's like it's dropped from. So you can kind of imagine from that, like, it's been sort of released, like someone's holding the ball in their hands, then they're letting go, they're dropping it. Okay, so you can imagine that at that instant, obviously it's held in someone's hand, and so it's released from 0 speed. Okay, so it's quite subtle, that is, but it starts again at 0 speed, and then obviously it's going to hit with a speed of v. Okay, I'm going to call that V0. Okay. And there we are. What else am I told? I'm also told the distance from the distance is 2.4 here. Okay. And of course the acceleration is 9.8. So if I use SUVAT, again, S is 2.4, U is going to be 0, V is V0, and A is 9.8. I'm going to be using V squared is U squared plus 2AS. So that's going to be V0 squared. It's going to equal 0 squared at 2 lots of 9.8, 2.4. So that means V0 squared, my V is going to be 47.04. And so if I root that, I get V0 to be 6.86. Okay, and there we are. So I can add that on. Okay, cool. And then of course it's then going to bounce back up. Okay, so then it's going to rebound, it's going to bounce back up. So it's eventually going to reach a speed of 0. Okay, and then it leaves the ground with a speed of u1. Okay, and there we are. I'm also told here that after it strikes the floor, it then bounces up by 0.6 meters. So this height here is 0.6 now. Okay, again the acceleration downwards is 9.8. so if I apply SUVAT again, I can actually just work out u1 here. So S is now 0.6. U is going to be u1, V is going to be 0, and A, again, that's going to be minus 9.8 because now we're going upwards. So acceleration downwards needs to be negative. Okay, again, V squared is U squared plus 2AS. So therefore, 0 is going to equal u1 squared plus 2 lots of minus 9.8, 0.6. So if we solve this, we get u1 squared to be 11.76. And so if we square root that, we get u1 to be 3.43. Okay, so there we are. Okay, so I can add that on, 3.43. Okay, so what do I need to do? I need to work out the coefficient of restitution. I need to show it's 0.5. So, okay, so let's consider when it hits the floor. Okay, so it hits the floor with speed 6.86 here. Okay, then it bounces up with speed 3.43. Okay, so E in this case is going to be the speed after 3.43 divided by 6.86. If I work that out, I indeed get a half. I get 0.5. And so there we are. Okay, and then in part B, it says find the height reached by the ball above the floor after the second bounce. Okay, right, so now we're going to need to consider another bounce. So now it's going to come back down again. So it's going to look like this. Okay, so it's going to bounce, it's going to drop back down to the floor with speed 0 initially again, right? And then it's going to reach with a speed of v1. And the height, well, the height again, this is after the first bounce. The height is now 0.6. Okay, so again the acceleration downwards is 9.8. So S here is 0.6, U is 0, V is V1, and A is 9.8. So that means that again V squared is U squared plus 2AS. So now V1 squared is going to equal 0, add 2 lots of 9.8, 0.6. So V1 squared is going to be 11.76. So V1, if I root that, I get 3.43. Okay, and there we are. Now, then it's going to bounce back up again. Okay. And then it's going to reach a height 0, a speed 0. Okay. And then it's going to leave with a initial speed u2. Okay, so now this is second bounce, so that's the speed after the second bounce. And so the height is what it wants me to work out. H here it wants me to work out the height. Again, the acceleration downwards is 9.8. So S is H here, U is going to be U2, V is going to be 0, and A is going to be, again, negative 9.8 because it's downwards, because now we're going up. So, well, we're going to need to work out U2 to work out H, but we can use restitution here, right? So now for the second bounce, so it approaches with speed 3.43, then it leaves with speed U2. Okay, so this is bounce 2 now, okay? Again, so E we worked out was 0.5. So 0.5 is going to equal U2 divided by 3.43. So therefore U2 is going to be 1.715. Okay, and there we are. So I can add that on here. So therefore now I can say, again, V squared is U squared plus 2AS. So 0 is going to equal 1.715 squared plus 2 lots of minus 9.8 lots of H. So that means 19.6 H is going to be 2.941225, therefore H 2.941225 divided by 19.6. That will get me 0.15. Okay, and there we are. 0.15 meters. That's the height after the second bounce, which is what they wanted. Then in part C it says, by considering my answer to part B, describe the subsequent motion of the ball. So it's very similar to the last question. So describe the motion. So we're going to need to again take into account the heights. So the heights are, now originally the height was it was 2.4, then it went to 0.6. So so it's 2.4, 0.6. Then we got 0.15, right? So the multiplier, or the common ratio, okay, or the multiplier, that's going to be 0.15, let's say, divided by 0.6, and that's going to be 0.25. Okay, so there we are. So that's saying we so the heights go down by 0.25 each time. Okay, or in other words, the height decreases by 25%. So the subsequent motion is the ball bounces with the height of after every rebound decreasing by 25%. Okay, or you could say, or by a multiplier of 0.25. So we multiply the heights by 0.25 every time. Or you could even say, or decreases by a quarter in this particular case, right? Because that's what 25% is. So yeah, so that's what they're looking for. So mainly they're looking for, when you're describing the motion, they want you to look for the height decrease, okay? So the how much it's going down by each time, so 25% or 0.25 as a multiple, okay? So there we are. So hopefully that's helped, but I'll see you next time. Okay, and the final set of problems we're going to be looking at, we're going to be revisiting bouncing off a wall, okay? But we're going to be looking at more deeper problems now. And actually, there isn't a section devoted to this in the textbook. There's not really anything on the textbook about this. So I think it's appropriate I do a little segment here, because it does come up in exams. So I want to go over this here now, okay? And so we're going to be looking at a particle or a ball bouncing from one wall to another, bouncing back and forth, kind of like what's going on here, right? And actually, to help you visualize, I'm going to play this little animation to see what we're kind of going to be looking at, okay? And so as you can see here, it's like a bit of ping pong, right? So we've got this ball going from one wall to another, okay? It's not going to look exactly like this, but hopefully you can illustrate the basic motion that's going on. It's being pinged from one wall to another. And so we're going to be looking at motion like this here, okay? And lastly, before we jump into our first example, we are going to be using distance, speed, time here, okay? Think back to GCSE. Remember that distance is speed times time, okay? And we're going to be using this because the speed is going to be constant, okay? In this whole chapter, we're going to be working with constant speed, okay? So when the speed is constant, we can use this formula here. So I'm going to say, because speed is constant, here, we can use this formula here, okay? So there we are. So we don't need to use SUVAT or anything like that, because that's constant acceleration. Constant speed we can just reduce to this simple formula, which should be very familiar with, okay? Anyway, let's have a look at our first example then. And actually, with this example, I've had to make it myself. Wanted to create a simple example just to go over everything step by step, okay? I think it's quite a good example to illustrate the concepts here. Okay, so here we're told a smooth particle is moving along a smooth horizontal floor. The particle from a starting point P is travelling with speed 5 towards a wall W1. The particle takes 20 seconds to reach W1. The coefficient restitution between the particle and the wall is 0.5. Now the first part wants me to calculate the distance travelled by the particle from P to when it hits the wall. Okay, so what is going on? So we need to draw something. Now what's going on here is we have a particle. Okay, again, we've got this little ball. It's at a starting point P. Okay, so my particle starts here. Okay. And then it's going to move forward. And then it's going to hit some wall W1. Okay. And there we are. Okay, hopefully happy with that. And I'm told it's travelling with speed 5 towards the wall. So I can label my speed here. Okay. So hopefully happy with this, okay? So, and also E is 0.5. I'll make a note of that. Now, the first part of the question, it wants me to calculate the distance from P to the wall. Well, actually, it's going to be this distance here, isn't it? Okay. What is that distance going to be? Well, actually, we know the speed is 5. It goes with speed 5. And we also know it takes 20 seconds to reach the wall. Well, actually, then we can quite easily use my distance, speed, time formula. So the distance is going to be speed divided speed times time. And here the speed is 5. And remember, it's a constant speed because it's always 5 between P to the wall. So it's a constant speed of 5 here. Okay, so 5 times the time, 20. Okay, so that gets me my distance of 100. Okay, and there we are. So the distance from P to the wall is 100 meters. Hopefully happy with that then, okay? And so that's the idea. We're just going to be applying my the formula to work out distance, time or speed or anything like that, okay? Then in part B, it says calculate the speed of the particle after it hits wall 1. So obviously you can see here it's going to hit wall 1 and then it's going to rebound. So that's where coefficient restitution will come in. So if I draw that scenario, so as we've seen, it approaches the wall with speed 5. And then it's going to rebound with a speed afterwards, okay? I'm going to call that V. Okay, I'll call that V. And I'm also told that E is 0.5, okay? So actually, I can just work out that E is going to be the final speed V over the initial speed 5. And actually then that means 0.5 for E is going to be V over 5. Therefore multiply by 5 I get V to be 2.5. Okay, so that is the speed it rebounds from the wall with. Okay, hopefully happy with that then. Okay, and then we're told the particle is now travelling towards an opposite wall W2, and the particle takes 56 seconds to travel from wall 1 to wall 2. The particle rebounds from wall 2 with speed 1. And so then it wants me to calculate the coefficient of restitution between the particle and the wall firstly, wall 2. So what's happening now is, after it hits wall 1, okay, so we draw this floor here. So the particle rebounds from wall 1, it bounces away from wall 1. Now the speed it bounces away from it is 2.5, as we just worked out. And so then at the other end, there's going to be another wall 2, okay, at the opposite end. And so it's going to keep moving forward, and then it's going to hit the wall, then it's going to hit wall 2 here, right? Now it's going to approach wall 2 with the same speed, 2.5, right? Hopefully happy with that, okay? So it's the same speed throughout, so 2.5 before it hits it. Anyway, now it wants me to work out the coefficient of restitution between the ball and the second wall. Well, actually, again, as you can see, it's going to hit wall 2. So if I consider that impact, so the particle is going to go towards the wall with speed 2.5. And so then it's going to rebound off the wall. Actually, we're told in the question that the ball rebounds from wall 2 with speed 1. Okay. So it's going to leave the wall with speed 1, okay? And so actually we can quite easily calculate E here then, can't we? So E, again, is going to be the speed after 1 over the speed before, or 2.5. Well, actually, that gets me E to be, if I work that out, 0.4, okay? And that's my coefficient restitution there, okay? So hopefully happy with that. Then part D says calculate the impulse exerted by the wall onto the particle. So again, remember we can also consider impulse in this situation. So if I look at this diagram again that I've got here with the wall, now again it's going to be impulse that's imposed onto the wall and the particle oppositely, right? So firstly, as you can see, that the particle is going to bash into the wall like this. So the wall's going to receive it. If I get rid of all this, the wall's going to receive an impulse in that way, right? Because the ball's going to push into the wall like this. And therefore the wall is also going to impose an impulse to the particle, okay? Which is opposite direction, which is also I, okay? And so we can now work out the impulse. If we consider the particle then, just the particle, we can see that the impulse is going to be, again, change in momentum. So that's going to be I is going to be mv take away mu, okay? Again, that's from chapter 1. So therefore, in this case, the mass Oh, we're not told the mass. I'm just going to say the mass is 2, okay? I forgot to include that, right? Mass is 2. My apologies. So if the mass is 2, so it's going to be 2 lots of V. Now, the speed afterwards is 1. Take away 2 lots of the initial speed, but that's 2.5, but it's going in the negative direction, it's going backwards. Remember, we always take positive forwards to be the positive direction, so we need to make this negative to account for the negative direction. So it's going to be minus 2.5 there. So if we work all that out, we get my impulse to be 7, okay, and that is Newton seconds, I believe. But there we are. That is my impulse there. And by the way, the impulse will always act like this, okay? Okay, the impulse will act like this, opposite to the wall. Okay, so hopefully happy with that, okay? Then for part D, it's part E now we're on, sorry, part E. Part E now wants me to calculate the distance between the 2 walls, okay? So if I go back to this diagram here between the 2 walls, right, it's this whole distance here, right? What's this whole distance going to be? Well, actually, we know the speed between the 2 walls is 2.5. And actually, we also know the time. It takes 56 seconds to travel between the 2 walls. So, in this case, distance is going to be speed of 2.5 times the time of 56. So we can work out the distance here to be 140. Okay, so 140 here. So hopefully happy with that. Then the final part of the question is saying, hence find the distance between wall 2 and the starting point P. So that's going to involve this distance here as well, which we considered in part A. So the distance from P to wall 1 is 100 meters. So actually point P is going to be, say, somewhere there. So that distance is going to be 100 meters. So then it wants the distance between wall 2 and the point P. So what's that distance going to be? Well, hopefully, if you look at the distances overall, the whole distance from wall 1 to wall 2 is 140, right? And then the distance from P to wall 1 is 100. So clearly, the distance from wall 2 to the point is going to be 140, take away 100. Okay? And so that will just be 40. Okay, so this is 40 meters here. And there we are. So that's the distance from wall 2 to P. Okay. And that's why it's very helpful to draw diagrams to for these sort of questions. Okay, because it'll help you to really it will help you to see and clearly work out all the information you have. Okay, and so there we are. Okay, now we've got an exam question. It's actually pretty similar to what was going on in the last question, but now there's a bit of algebra and a bit of fluff. Okay. So we've got this diagram here. We've got 2 walls here, and then we've got this particle here that's going to go between wall 1 to wall 2, essentially, right? Basically, we're given all the information really on the diagram, really. So what's happening is the particle starts at O, then it's going to move towards wall 1, bounce from wall 1 back to wall 2. And then it's going to return from wall 2 back to O. Okay, so it wants the whole time of that whole journey. Okay, so we need to get to this expression here. Okay, and actually, instead of doing a bunch of different diagrams for the different parts of the journey, I think it'd be better to do just one big main diagram. So I'm basically pretty much going to copy what they've done here. So again, I've got this floor And then I've got the two walls. Okay. Wall 1, wall 1, wall 2. And so I have my particle here, it starts at O. Okay. And then I'm basically just going to do the journey. So it firstly goes towards wall 1. Okay, and it goes with speed U. And then it ends up at wall 1. Okay, so this is my first part of the journey at the starting point here. Then it goes to wall 1. And then it's going to approach it with the same speed U. Okay. Then it's going to rebound from wall 1. And then it's going to go to wall 2. Okay. And so that's going to be my third part of the journey. So you can kind of piece the timeline here. So we start here. And then we end, then it hits wall 1, then it goes all the way to wall 2 at my third point. And there we are. And then it's going to go from wall 2 back to my starting point. So then this is going to be the fourth point of the journey here. So hopefully happy with the timeline. Now we're going to label all the information. So we're told the whole distance from the walls is 3. So let's add that on, okay? So all of this is 3 meters, but also I'm told the distance from the starting point O to the wall 1 is D. So this length from point 1 to point 2 is D. Okay. And so there we are. And then you can actually work out, because we laid it out so nicely, we can also then work out an expression for the distance from point 3 to point 1 here. Well, if the whole length is 3 and then this length is D, it's going to be 3 take away D here, okay? And that's why it's very helpful to do a diagram like this, okay? Really recommend you do it like this, because then you can clearly see all the information. Okay, now I'm going to label my speeds. Well, it starts with speed U and then it's going to approach the wall with the same speed U then, right? Then it's going to rebound off the wall with a speed afterwards, right? Here. Now, how am I going to work out the speed afterwards? Well, again, I'm going to use coefficient of restitution. So in the question, I'm told that E is 2/3, okay? And so you might think, well, to work out the speed after the impact, do a different diagram, right? I don't need to do that, really. I can just do it in my head, because what E is effectively saying is how much I'm reducing the speed by. So if I'm going with speed U, I need to then leave with speed 2/3 of U, okay? And there we are. So it's going to leave the first wall with speed 2/3 U, and it's going to then approach the second wall with that same speed, okay? And then it's going to rebound off the second wall. Now again, E is 2/3. In this case, it's the same coefficient of restitution. So I'm going to multiply by another 2/3. So it's going to be the speed afterwards of 4/9 U. Okay, and then it's going to then return back to the starting point with the same speed 4/9 U. Okay. And there we are. So hopefully happy with that. So I really do recommend doing the question like this. Just one diagram, label all the key parts of the journey. So it starts at point 1, hits the wall at point 2, then it goes to the other wall, point 3, then returns back to the starting point at point 4. Okay. And so I've labelled all my distances and the speeds. Okay. And so this makes it really easy to work out all the individual times involved, okay? So we want the total time of the whole journey. So we're going to need to split it up for each part. So firstly, the time from point 1 to point 2. Okay, so time. Now remember, time is distance divided by speed, okay? Remember that formula? So in this case, the time, so from point 1 to point 2, we can see the distance is D and the speed is U. Okay, it approaches the wall with speed U. So it's going to be D over U. Okay, and I can't do anything more with that, okay, but that's my expression. Then the time from point 2 to point 3. Well, again, time is distance over speed. Well, from point 2 to point 3 is the whole 3 meters here, right? So it's going to be distance of 3, and the speed, well, it leaves the wall with 2/3 u. So the speed is now 2/3 u from wall 1 to wall 2, okay? And there we are. Now, actually, we can simplify this. It looks quite ugly, right? A fraction in a fraction. If you're struggling with this, we can say this is 3 divided by 2u over 3. And then think back to GCSE, dividing fractions, keep, flip, change. So 3 times 3 over 2u. So that simplifies to 9 over 2u. Okay, and so there we are. Then we can lastly work at the time from point 3 to point 4. Okay, so in that period, the time is going to be from point 3 to point 4. You can see the distance is 3 minus d divided by the speed at that period of time. Well, it leaves wall 2 with speed 4 over 9u, and so there we are. So my speed is 4/9 u. And so we can simplify that. You should get 9 lots of 3 minus d over 4u. Okay, and actually we can expand this to get 27 minus 9d over 4u. So these are my times of each part of the journey. So therefore the total time, you just add all these up. So it's going to be d over u first, and then 9 over 2u, and then lastly 27 minus 9d over 4u. And then we just need to simplify this expression. Well, I can get a common denominator of 4u, so I'm going to need to multiply the first fraction by 4, so 4d over 4u, then the second fraction by 2, so 18 over 4u, and then 27 minus 9d over 4u. Then I can just simply add. Okay, so 4d add 18 plus 27 minus 9d over 4u. And if we simplify that, we get 45 minus 5d over 4u. And actually, if that's the time t, that should be the expression they wanted. Yes, it is. We got it right. So that's the core idea, right? So do a diagram like this. So do all the parts of the journey, label your distances and your speeds, and then you can work out your relevant information quite nicely. Okay. Okay, then we're told the value of u is fixed, and the particle still hits each wall once, but the value of d can now vary. Find the least possible value of t, given it in terms of u. Okay, this seems a lot harder than it actually is, okay? The question seems really weird. It's probably designed to put you off, but all it's saying is, if we keep u the same, okay, so this is my expression, right? T is 45 minus 5d over 4u. If we cannot change u, okay, we can only change d. Only d can vary in value. So what is the least possible value of the expression t if we can only change d? If we just stare at this fraction, then you can see we need to increase d as much as possible, because we're going to be taken away by 5 lots of d. So if that's the only part we can change, we're going to want to increase d, so we subtract by a big number. Hopefully happy with that. So I'm going to say to increase t, or increase the value, decrease the value of t. We want to increase the value of d. Okay. And yeah, so don't try and think about it too deeply. Simply, if you increase the value of d, take away by a bigger number, therefore the whole fraction goes down. That's the whole idea, okay? Try not to overcomplicate it. Well, okay, so we want to increase the value of d as much as possible. Well, actually, if we stare at the question, we're told that d can only be between 0 and 3. So the maximum value of d equals 3. And that's really it, okay? So therefore the maximum value of d is 3. Therefore the minimum value of t, if we sub d's 3 in, is going to be 45, take away 5 lots of 3 over 4u. If we simplify this, we get a t to be, in this case, to be 15 over 2u. Okay, and there we are. That's my minimum value for the t there. So there we are. Again, a very weird question that is, but there we are. So hopefully that has helped. So remember, the whole idea is we want to sketch what's going on. So we sketch all the individual parts of the journey, then label all the distances, the times and the speeds. Then we can work out all the missing information based on my label diagram, and also using distances, speed times time to work out anything out. And that's the idea, right? So it looks scary, but if you just piece all the information together, draw a nice diagram like I've done, you can work out anything that's necessary. Okay, but there we are. I'll see you next time.